Okay, so we are going to, again, we're going to evaluate these two line integrals in two different vector fields. The first vector field, negative 2y. Second vector field, negative 2x. First path is C1, one counterclockwise trip around the unit circle. C2 is going to be a clockwise trip around the triangle, which consists of three line integrals that we add together to get the whole single line integral. So to parameterize this segment right here, if we're starting here and ending here, there's a way to do this so that your start point is t equals 0 and your end point is t equals 1. You don't have to do it this way, but this is really convenient. It makes your bounds of integration then will be from 0 to 1, which is really convenient. And there's a zillion ways to parameterize this. So as long as you have a way that works and you get the right limits of integration on your integral, it's fine. But this particular way is nice, so I'll do it over here. So when t equals 0, we have what point? We want the vector for t equals 0, we want the point 1, 1, right? And when t equals 1, we want the point down here. In this case, negative 1, negative 1. So to write these formulas, so to write, say, RT, there. Okay, so to write RT, so we know we want to get 1, 1 when t equals 0. So we can just write down 1, 1. Because when t equals 0, we want to get 1, 1. And so then all we need to do is figure out what our coefficient of t is to make this work, to get the final point right. Because it's linear, so it's going to be, each component will be linear. So when t equals 1, we want to have negative. By the time we get to t equals 1, we want this whole thing to be negative 1. So what do we need that coefficient to be? Negative 2. And what does that negative 2 represent then? What does that negative 2 represent in this situation? Well, it's the rate of change of x with respect to t. It's not the rate of change of this, right? Because this is an xy. So what does the negative 2 really mean?
The vector.
The vector, okay.
The vector of the line.
Yeah, so it's like in x, it's like as you go from here to here, what happens to x? Right, so it's like the vector. It's like the change in x is negative 2, right? This is your change in x negative 2, so that when t is 1, you'll have the starting point plus the amount of change, right? So what about y? In this case, it's the same thing, right? So y changes by negative 2 as well. So we'll start at y equals 1, and then we want y to change by negative 2. So this is a nice way to parameterize. So you've got the starting point when t equals 0, and then you have how much x changes and how much y changes. If you have a different way of parameterizing a segment, as long as it's right, be my guest. Okay, but we'll use this one for this problem. So the rest is up to you. So I want you to set up, I want you to finish parameterizing this, and let's use S here and U here so we don't get confused. Right, so you're going to have a new parameterization for that line, so let's use parameter S and parameter U for the horizontal one up here. And then we could use for the V, we could use parameter V for the C1. So use V parameter for C1, use S for this second leg of C2, and U for the third leg of C2. I just want you to finish parameterizing these paths. So this is what we said, this is C1, the blue one is C2. So finish parameterizing C2 and parameterize C1 and get the limits. Get your limits of integration, and then we'll go from there. So You could use this technique on these two, but it's these two are a lot easier than that. You don't have to work through this technique to do those two. So hopefully these are just intuitive. You just kind of write these down. You don't have to work through all this stuff. That's the goal anyway. Okay, and then once you get those, then we want to start writing out the line integrals, okay? For the two different fields and two paths for each field. So I'll give you about 5 minutes, see how far you can get. What is RV? Hopefully we all got that one. The path C1. What is that? Sarah? Cosine, we're using V, right? Sine V. Did you guys get that? Unit circle should have that. We already did the first leg of the triangle. So second leg of the triangle, S. So what do we know right away about S here, about this path? Not true. That's not true. You're identifying all these points. There's no change in X. But what is X? Always -1. So you just write -1 down, right? And then, so what changes? Y. So you can just say S. And then get the limits right? The limits will be from what to what? -1 to 1, right? -1 to 1. So you just do -1 S. Should be an S. So yes, there are techniques and formulas, but then there's just understanding, which is, buys you a lot of time and effort. But by just knowing what you're doing here is you're defining all points. You're defining all points on this. Well, all x coordinates are -1, and then the only thing that's changing is y. So call y S. Same thing with this. So what would this be? U. X changes, U, and +1 is Y, right? Okay, so we got that. So now we're ready to go. So vector field number 1, path number 1. What is the line integral? How do we do? Rebecca, did you get this?
Yeah, so I got 0 to 2 pi.
Integral 0 to 2 pi.
And then it was -2 sine of v minus cosine v minus sine v.
So is this after the dot product?
Yeah, after that.
After the dot product, you get -2 times
sine v
sine v
minus cosine v sine v.
Someone else get that? And then it's going to be dv. Did someone else get that?
Oh yeah, it's a positive too.
So you're finding you're agreeing with that? Is that what you're?
No, it's positive 2. So yeah, plus cosine.
So dr would be -sine v cosine v times, so it's positive. So both are positive. Now do we have it? Is this right now? No?
Oh yeah.
I've got one nod. Does everyone see where we came up with that line integral? Right? We did the dot product of what? The -2y dot dr. So I skipped some steps there. Okay, how about path C2 for vector field 1? And who wants to give that a shot? You want to give that a shot? Or just how about the first part of it? Okay, you forced my hand. Lauren, did you get it?
Uh,
How about just the first part? Did you get it? The first part of that line integral? No? Okay. You still got it. Yeah, Andrew.
0 to 1
Uh-huh.
and negative 2 are going to understand the vectors. I don't know what's actually
Well, to get a value here, I need to have those multiplied out.
well, it would be 4 minus 2 plus 4t.
Like that? dt. Okay, and so that's the line integral down the diagonal. Anyone want to do the second part of this? David, did you get the second part of this? This David here. So what are we going to go from? S is going to go from what to what? S goes from, on this second piece over here, negative 1 to 1 of what? Negative 2 times 0 plus S times 1, so just S, ds. Is it right? Are you guys checking with me? I'm not seeing much response here. I'm not getting feedback from the faces or the heads.
Yeah.
Is it right? Paul, do you agree with that? All right, so it would be what? Negative 2, the vector would be negative 2, and then y would be s, right? Dot 0, 1. So we just get s, right? Because we get negative 2 times 0 plus s times 1. I think that's right. Last leg of the trip. We're going to go from negative 1 to 1. And so we're going to have negative 2 times 1 plus 1 times 0. So negative 2 d, what do we call that? du? Did I lose you? I skipped steps. Okay, I skipped steps, but this is just like your homework. You did all this homework for today, so it should be following it. Okay, so let's notice what happened here. So we went around the circle, and what was the value of the line integral?
Very close to 0.
Yeah, it's essentially 0. So the way that this GC is calculating with these sines and cosines, that's 0. Okay. And then what about when we went around the triangle? 0. Okay. So what about, let's do in vector field 2, let's do path 1. What should we get?
0 to pi.
This time's going to be 0 to 2 pi. And now in vector field, so it's negative 2 and what? Cosine v times negative sine v cosine v. So what does that turn out to be?
Sine v, or 2 sine v.
2 sine v minus cosine plus cosine. Is that right? Agree? Cosine squared? That's it. dv? Is this line integral right? So we'll just go ahead and do it. dr is negative sine v cosine v. And our vector field is negative 2 cosine v. So dot product, positive 2 sine v plus cosine squared. That's right. You're giving me the eyes, Julia. What's that?
vector field number 1, the first
Path C1?
first C2, sorry.
Down here?
Yeah.
This one right here?
Yeah. So you want, okay. I thought there would be a square in there somewhere.
So our dr would be negative 2, negative 2.
Oh.
And then we'd have negative 2, 1 minus 2t. You good? You good?
All of that.
Okay. All right. And so we got 0, right? Because we went around the loop again. Oh, wait. Okay, different field. So this field, when we went around a loop, we tried 2 different loops. We got 0 and 0. And for this one, we went around a loop and didn't get 0. We're not going to take the time to do vector field 2, path 2. Okay, so we got to move. All right, so this time we went around the same loop and didn't get 0 anymore. So what's going on here? What's going on? Marvin Gaye, what's going on? Yeah.
It's going in the same direction for a longer part of it, so it actually accumulates.
Oh, so you're just looking at the vectors?
Yeah.
Okay. Yeah. So if we look at this, yes, we could look at what's happening and kind of reason that things would cancel out and you get 0. And here you got a lot strong positive and then kind of 0 and then only a little bit of negative. Yep. Okay. But why does one give loops that have a line integral of 0 and the other doesn't? Yeah.
Because the first one is mirrored and the other one isn't.
Okay, so we have symmetry. There's some kind of symmetry about this vector field where we get this canceling effect. So what about these 2 fields? Griffin, did you want to share something?
It's a conservative vector field.
What's that?
All vectors have the same value.
Not quite, because when we change y values, we get different values. So remember we analyzed vector fields for something, right? What do we analyze vector fields for? What's that?
Gradients, right?
Yeah, is whether they're a gradient field. So is this a gradient field? This one. How can we tell? If it is, then what is negative 2? The partial with respect to x. And y is? Partial with respect to y. So is there one function f that has those partials? So what would this would give us one perspective on f, which would be what? Negative 2x. Plus, could be some function of y and a constant, right? This gives us some perspective on f. Y squared over 2. Does this function have this as its gradient? Yes. So this is a gradient field. How about this one? This would tell us that, so if we were trying to put together this thing, from this perspective, f would be negative 2x. From this perspective, it would be xy. Does it work? No, because now when you do the partial with respect to x, there's a y here that you don't have. If it were negative 2 plus y, you'd be golden, right? You'd be fine. But you don't have this plus y. So there's no way to write a potential function like this, a multivariable function, whose gradient is negative 2x. Not a gradient field. It's worth thinking about. Okay, so that's not a gradient field. So what happens in a gradient field is, what happened if we think of this as work? If we think of this as work around the circle, so the field is doing work, and what's the net work that we do going around the loop? 0. So energy is conserved, right? So when you make it back to your original spot, whether you take the blue path or the red path, energy is conserved, and so gradient fields are called conservative because it's of the conservation of energy. Gradient fields are conservative because if you were computing the work around a loop, the sum of the work would be 0. You have conservation of energy. The work, so in other words, the work that the field does is the same as the work that the path puts back into it, right? So in the first part of this circle, the field is doing what kind of work? Positive. The field is actually doing work. In the second part of the loop, the work is negative, meaning that whatever's traveling through this is like putting that energy back into the field, right? That's what a field doing negative work. It's like getting work from whatever's moving through it. And so those balance out, and you have conservation of energy. Here you don't. We have this field does all this work, it doesn't get it back, right? So it maybe gets a little bit back down here at the bottom, but it doesn't get as much as it gave here. So this is not conservative. If it's not a gradient field, it's not conservative. All right, so conservative vector fields have a potential function. They are gradient fields, and they have a potential function from which that field came. There's no potential function that can create this field. So it's not a gradient field, it's not conservative. Okay, so let's take that conversation a step further. Any questions on that? What happened? Do you understand? Does that make sense? Okay, so let's look at this then. Same field. Oops. Okay, there we go. So now, this is the path in the first quadrant around a circle with radius 3. So here's where we're going to start here. We're going to end here. So what will our R be? So R of t will be 3 cosine t, 3 sine t. dr will be negative 3 sine t, 3 cosine t. Our field is, in terms of t, negative 2 and 3 sine t. Line integral would be 0 to pi over 2 of f dot dr. So we get positive 6 sine t plus 9 sine t cosine t. Did I do the math right? Is this going to be positive or negative? What do you think? Clearly from the picture, the field is going to push us along, right? The field is going to do work. It's going to push us along. It ends up being positive 10.5. I know that from before. So. I didn't do it, but it's 10.5. Okay. So now, I want to do a new path. I want to calculate the line integral starting at that ending point. I want to know the line integral from here to here along that blue straight line path. What's the value of the line integral? I'm done. Anybody else done? Griffin has it. Matthew has it. Eric has it. Alex has it. Alex, what is it? Negative 10.5. Why is it negative 10.5? So this line integral right here along C2 of f dot dr. Tell me, why is it negative 10.5?
Because it's closed loop on a conservative field.
We're still in the same conservative vector field, right? This is that gradient field, negative 2y. So what is that line integral of that loop? What would that line integral of that loop be? 0. So if I told you this was positive 10.5, then what does that have to be? Negative 10.5. See? Okay, how about this? So now I'm going to go along this path. this straight line path like that through this vector field, and then down like that. So this is C3, f.dr. Who's got it? What is it? No, this C3, so from there to there. Negative 10.5 again. Why? Because that makes another loop, right? So that's 10.5. To get back to your starting point, negative 10.5. Okay, I got one more. Ready?
Negative 10.5.
No, you're wrong.
Now.
I'm going to go this way. So I'm going to start here, and I'm going to go like this to get to here. What will that be? That's positive 10.5, right? It'll be the same as this red one. So conservative vector fields are? That's not what this showed. Conservative fields are what's called path independent. Path independent means given a starting point and an ending point in a conservative field, no matter how you get from A to B, no matter how you do it, it'll be the same amount of work. Right? It'll be the same line integral from A to B. If A and B doesn't change. As soon as you change A and B, you get a different line integral. Okay? But with the same starting and ending point, every path gives the same line integral. Written homework's due Friday. Written homework's due Friday.